Let's consider a simple example system to get a better idea of what our root locus actually looks like. So in this example, we're going to consider the tracking system for a security camera. And so it can be represented by this block diagram shown below. And so we can think of our input as being some subject position. So maybe somebody's walking across the field of view of the camera, and we want to track that person for some reason. So this is our subject position. And then of course our output is going to be our camera position. So based on where we see our person or whatever it is we want to track, we want to move our camera in line with that. And so of course we're going to have some sensors that are taking that input and combining it. And then we have some amplifier here represented by a gain K1. And this is going to be our motor and camera. And so it's good to keep in mind that behind all of this heavy math that we're doing, there are actual physical systems, and pretty much anything in engineering is going to have some type of control system associated with it. So using techniques we've seen before, we can reduce this to one equivalent transfer function. And so that function is just going to be K, and so I'm simplifying, and I'll define that in a little bit, divided by s squared plus 10s plus k, and we have our input r of s coming in here on the left, our output c of s coming out here on the right. And so in this case, I've just defined k, which is equal to k1 times k2. So let's sort of take a step back for a second and say, what is our goal with this root locus technique? Well, ultimately what we want is a graphical analysis tool. So graphical representation, and what is that graphical representation of? It's of our closed loop poles as some parameter is changing, in this case gain. So representation of the paths of our closed loop poles as our gain is varied. And so for now, what we're going to say is let's keep that gain greater than or equal to 0. Later on in the unit, we're going to come back and see how to deal with the case of negative gain. And so what we're going to see is that actually takes this negative feedback and makes it a positive feedback system. The other thing that you might be thinking is, well, in the first video, didn't we say we didn't have to find this closed loop gain explicitly as we've done here? And so that's true. And so that's something we're going to come back to later as well. But in this case, for our example, we're just going to have this closed loop gain, and we're just going to sort of brute force it. But a little later on, we're going to figure out easier ways where we don't have to solve for that equivalent transfer function t of s. So we're going to brute force this example. And so what do I mean by brute force? Well, we're going to consider our denominator of this equivalent transfer function, this s squared plus 10s plus k, and we're just going to vary that k value and see what our poles are. So because this is a second order function, a second order polynomial in the denominator there, we know we're going to have two poles. So I'm going to write some values from a table in the textbook, and so these are going to be pretty easy to sort of confirm as well. So we're going to have a gain value, a pole 1 location, and a pole 2 location. And so the select values I want to look at are a gain of 0, a gain of 10, 25, 35, and 50. And so if you look in your textbook on page 311 in the 8th edition, these are excerpts from table 8.1, and there are some more values in that table if you're curious. But again, I don't think you necessarily need to. I think I've chosen sort of the important ones here. So of course, let me go ahead and write this function down here so we can see it a little easier with our table. So if we have k equals to 0, then we can just factor out an s of s squared plus 10s, and we can have one pole, which is going to be at negative 10 from the s plus 10, and one pole is going to be at 0 from just our s term. Now, if we have a gain of 10, we're substituting 10 for our k. We could then use quadratic equation or MATLAB or any type of calculator to figure out our two poles are going to be negative 8.87 and negative 1.13. If we have a gain of 25, again, we use MATLAB, quadratic equation, whatever approach you want to do. We're putting 25 for our k, and what that's going to give us is negative 5 and negative 5. Keeping on increasing our gain, so now at 35, we're going to have negative 5 plus j 3.16 and negative 5 minus j 3.16. So now we have a complex number for our two poles. And then the final entry we're going to consider here is negative 5 plus j5 and negative 5 minus j5. Okay, so again, there's some more values in that table in the textbook, but I think this is good enough to start sort of getting an idea of our root locus by sketching those values, or sketching our pole locations, which ultimately, again, remember, is what our root locus is. So let's sketch our pole locations. So let me go ahead and paste this plot here. So what we're saying is, let's start with our gain of 0. And so for our gain of 0, we have our poles are going to be at, and let's do this in green, I think, are going to be at negative 10 and 0. So if I come down here, I've got sort of little markers, so we can count out here is going to be 10, so negative 10, and here is, of course, 0, so this corresponds to k equals 0. Now, if we increase our gain to 10, we see our poles are going to be at negative 8.87 and negative 1.13. So let me switch over to red. So negative 8.87, so that's just below negative 9, so somewhere around here, and negative 1.13, just a little above 1, so we're going to be somewhere here. So that is for our gain equal to 10. So let's switch colors and do another one now. So let's go to purple. So our gain of 25, we have two poles at negative 5. So 1, 2, 3, 4, 5. So we're going to have sort of real repeated poles right there. And so that's going to be our k equals 25. And let me move that out of the way a little bit. Okay. And so let's keep on going. We've got a few more. So let's do brown. So now if we do 35 for our gain, we have negative 5 plus or minus j 3.16. So 3.16, so a little above 3, so somewhere about here and about here. So that's a k of 35. And then finally, let's do pink for our gain of 50. We have negative 5 plus or minus j5. So we have a pole about here and about here. Oops. And so that's going to be our gain of 50. And so what we can see is sort of our root locus is going to show us the path of these closed loop poles as our gain is changing. And so we can see that we start here at this negative 10 and we're moving in this direction. Similarly, we're starting here at 0 with the other pole and we're moving towards this negative 5 as well, staying on that real axis. Once we reach negative 5, those two paths break away from our real axis, and one is going to go up, and so that should be straight up. Let's see if that'll, there we go. So I've drawn the X's a little off, but that should be a vertical line going straight up, and then we'll have one going straight down, because again, of course, those both have the same real parts of negative 5, so those again should be basically a cross here, vertical line, horizontal line. And the big takeaway here is that we see the direction of our poles, so we have them going inward, and then one up and one down. So there's a couple things that we can observe from this then. So we can talk about our response type, we can talk about our sort of specific values of our response as well. So we can note that the response is going to be overdamped for k less than 25. So response is overdamped for k less than 25. And so the reason we can say that is because for k less than 25, we're on the real axis, or our two poles are on the real axis. Once we're at that 25 point, it's going to be critically damped because we have real and repeated poles. So critically damped for k equals 25. And then once we break off of the real axis, so once our gain goes above 25, we now have two complex poles, so that means we're going to have an underdamped response. So, and underdamped for k greater than 25. So all of that information we got from our root locus just sort of by glancing at that relatively quickly. Another important thing that we can see, so this is sort of one area that we could look at. Another important thing that we can see is that our system is going to be stable for all gains. So system stable for all gains, k greater than 0. And the reason for that is because our poles are always in the left half plane. So always in our left half plane. So no matter what the gain is, and again, keep in mind that this should be a vertical line, it's not actually going towards j omega, we're never going into our right half plane over here, which we would need to do in order for the system to be unstable. So we can go a little further even, and we can talk about what's happening in the underdamped portion for our k greater than 25 as well. So let's consider that. So let's consider our underdamped portion. And so this is again going to be for our k greater than 25. And so what we can see is that our damping ratio is going to be decreasing as our k increases. And so there's a couple different ways we can think about that. The first is the relationship to our percent overshoot. And so we know that our percent overshoot is going to be increasing because, as we've talked about in a previous unit for our time response, our percent overshoot corresponds to a constant radial line. And so if our radial line where our pole location is increasing like this, that corresponds to an increasing percent overshoot, and conversely a decreasing damping ratio. Another way that we can think about that is going back to our initial equation here. So we have this s squared plus 10s plus k. If we compare that to our characteristic equation sort of in our general form, we have s squared plus 2 zeta omega n plus omega n squared. And so what we can see is, comparing that, our omega n is square root of k, but our 2 zeta omega n is a fixed value at 10. So we can come down here and we can say our omega n is equal to square root of k, but our 2 zeta omega n is fixed at 10 in this case. And so what that means is that if our k is varying, our omega n is varying, but because this has to stay at 10, with our omega n increasing, that means our zeta has to be decreasing. So again, all of this information we're just getting from our plot relatively quickly. What we can see is a couple of other things based on the location of those poles is, because once they're underdamped, they have the same real part. So as our k is increasing, we know that means we're going to have no change in our settling time. So no change in our T of S. And again, that goes back to the relationship we looked at. We said vertical lines in our S-plane have the same settling time. So because we're on sort of a vertical line for k above 25, we know the settling time should be the same. We also know that we should have an increasing, or we do have an increase in imaginary part, which is going to correspond to a reduced peak time. So increasing imaginary part as our k increases means we have a reduced peak time T sub p. And so that corresponds to, we said we have constant peak time for horizontal lines, and that peak time is decreasing as we get larger. So we can see that's true as we're increasing our gain. And so for all of that stuff, if that was kind of a little confusing or maybe you don't remember it as well, you can go back to the notes, so pages 310 to pages 317, and particularly that page 317 has that relationship of these characteristics, our TS, our TP, and our percent overshoot, to our location of the poles in the S-plane. And so what we can see is happening with this function is it's having the same settling time over time. So let's do C versus T. And so let's say we have some final value here. And so basically what's happening is we're saying let's just draw sort of our initial value here, and we're saying our peak time is getting quicker, but we have more overshoot and we have the same settling time, so it's settling out at the same time as we're increasing our gain. So sort of just trying to connect all of these ideas of our time response plot, our plot of our pole location in the S-plane, and then of course we can relate that back to our block diagram. And ultimately, remember there's some physical system behind all of this math too.